Good morning, Matthew Ward here with Ward Engineering. In this video, I am going to teach the system that I use for completing projects that involve the seismic anchorage of non-structural components. So essentially what I'm going to do is I am going to do a start to finish video that shows exactly how I create the plans and structural calculations for the anchorage of this particular tank here for a laboratory out in the Bay Area of California. A little bit of project information is that the tank that we're going to be looking at is 1,671 pounds. It's about 3.5 feet wide, 10 feet long, and about 4 feet tall. There are 4 anchoring points that we'll be using 5/8 inch anchors, and it's in the zip code of 94588, which is important because that's a high seismic zip code of California. Really, I have 2 objectives here for the course. Number 1 is to teach you how to prepare the equipment anchorage plan, which is going to be 1 sheet and look something like this. And then objective 2 is to teach you how to do the structural calculations, which will end up being about 18 pages. One of the key philosophies that I like to employ when doing my projects is to start with templates. So as you're going to see in this project, there are 4 templates that I will be using. I have 2 AutoCAD templates, I have a Microsoft Word template, and then I have a Microsoft Excel template, which I use for the anchor design and slab overturning. So in general, I want to let the templates be my guide. I never want to reinvent the wheel. I never want to have to really work harder than is necessary, and if I've already put the work in and created a workflow, I want to use that on subsequent projects. All of the templates that I will be using are available for purchase at the Ward Engineering online store. So you'll see the 4 templates that I just mentioned are here, and you can order them here through the store. And once you see me complete this project and you see the power in these templates, then you'll better understand their value. Here's my contact information. If after watching the video and seeing how the plan and calculations are put together using the templates, if you want to reach out to me with any questions, feel free to reach out to me and I'll be happy to help you out. So with that being said, I'm going to jump right into it. So to get started here, first off I want to start with my project folder. So I'm going to call this project ABC Labs. I'm not going to put the real name of the laboratory. So we'll call it 2301 ABC Labs Tank Anchorage. As I mentioned previously, I have 4 template files. So I have 2 AutoCAD files here, and I have my template file for my Word document here, and my template file for the anchorage calculations here, an Excel file. So there are 4 files. Those are my templates I'm going to get started with. First file that I'm going to open up here is going to be my Word document. So I'm going to rename this one. So call this 01, the first project of 2023, and we'll call it ABC Labs Tank Anchorage. So I'm always going to start with my Word document, and I'm going to let the Word document be my guide. As far as the project name, the name that the architect has asked us to use for this project is New Exterior Air Tank Installation, and then for the location I'm going to just call it ABC Labs. You can see we already have our table of contents. We already have a lot of the sections set up, so that way I can easily replace information. So another one of the key philosophies I like to use is that it's easier to delete information you don't need than it is to recreate information you do need. So when I'm setting up my templates, I set them up with that in mind. Okay, so I'm going to give this the same name that I previously put on the cover sheet. New exterior air tank installation, say for ABC Labs. And this is project 2301, so representing the first project of 2023. Project description, we'll call it just normal equipment Anchorage, and we'll call it 123 drive, and the zip code that this is gonna be at is 94588 in the city of Pleasanton. And most of the projects that I'm doing for GRA architects, so I just leave this information in here for most equipment Anchorage projects. I'm typically working with this company here. And as far as the building code information, okay, so it will be, these are the standard codes in this current code cycle in the year 2023. The jurisdiction that we're going to be using is the city of Pleasanton. So at this point I would typically just go online, do a search, and find their information. So I'll throw this off over here to the side. So say city of Pleasanton, building and safety division. And their address, based off of the website. And we don't currently have a contact person, so I'm just going to delete this row, and all I'm going to do here is I'm just going to put the phone number, so based on the website, the phone number 925 931 5300. And then here, since we don't have the contact information, I'll just put the website. Alright, so there we have it. We've completed our first page here. Now moving on. Geotechnical criteria. If I was provided any information regarding a soils report, like allowable soil bearing pressure, I'd put that here. However, I don't have any information, so I'm just going to put NA here. Okay, now loads. This is where I am going to put in any dead and live load information. So, as we were talking about earlier, this project is regarding a tank. So the tank that we're talking about is this tank here, and you can see that it has a shipping weight of 1,671 pounds, and the tank will be having air in it. So as far as a dead load, I'm just going to simply use this number here. If this tank was going to have water in it or something like that, like a liquid, then I would want to calculate what this thing weighs with that liquid inside of it. But for the purpose of this project, we're just simply going to use that shipping weight information. So I'm going to put the name of the tank in here, and it's a horizontal air receiver. And call it a tank. horizontal air receiver tank. And the weight of this thing is 1,671 pounds. And the tank will be filled with air, so I'm going to use the shipping weight. Okay, now I would want to insert a little clip of what of where I came up with that weight. So what I like to do is I like to use my clipping tool, which is called, I think what do you call it, snipping tool, and I take a screenshot of the take a screenshot of the weight information, and I'm going to put that here in the report. That way, if there's ever any question about, well, where did I come up with this number, then I've got this here to remind myself of where I got it. Snow. There won't be. First of all, there is no snow load information. No snow load in Pleasanton that's used. As well, this tank is going to be indoors, so snow load's irrelevant. Likewise, the same with wind. So this tank is going to be inside a building. So for wind, I state NA. The equipment is within the building. So as far as lateral loads, the lateral loads we're concerned about obviously are seismic. The next thing that we are going to do here is pull up our seismic load information. I like to use ATC hazards is my go-to, and the zip code out here is 94588. So I can come here to seismic, select ASCE 716 as my reference document. This place would be a risk category 2 location. The site class, I don't have a soils report, so I'd be putting D for default. And then I come here to print these results. And I'll zoom in on the information I'm interested in. Really, the only piece of information that I'm really interested in here is SDS. That's your short period seismic acceleration value. And in this case you can see it's 1.55, so that's very high. So 1.55 times gravity is the short period seismic acceleration for this site. Alright, so I'm going to take a screenshot of this, and I'm going to throw this into my report. So here's my report. So I'm going to take out this previous screenshot. I'm going to put in my current screenshot. So there we have it. And here is a screenshot from ASCE 716, table 13.6.1, or -1. And I highlight the AP, RP, and overstrength value for pressure vessels not supported on skirts. So this is a screenshot that I'm using to show where I'm getting these values from. So for various pieces of equipment, whether it's mechanical or electrical or architectural, there are varying AP, RP, and overstrength values that you need to know. And for this project, ours will be, the AP will be 1, RP is 2.5, and overstrength is 2. And all of that is discussed in great detail in Chapter 13 of ASCE 716. Now, for the purpose of this video, I'm not going to go into talking in great detail about that chapter. However, you should familiarize yourself with that chapter if you're going to be doing designs with that section of the code in mind. So here's the main equation that we're talking about, the FP value, the horizontal force that'll be acting on the tank. is this equation right here, which shall not be taken greater than this value or less than this value. Alright, so the next step I'm going to do here is I'm going to turn to InterCalc, and I'm going to do the calculation for FP in InterCalc. So I'm going to create a new project. I call it 2301 ABC Labs. Alright, so I'm going to come here and I'm going to go under Seismic Loads and Forces, Seismic Demands on non-structural components. That's what I'm interested in here. Alright, so the first thing I'm going to do is I'm going to enter my SDS value. So, as I previously stated, the SDS value for this particular site is 1.55. So I'm going to throw my Word document over here to the side. I'll type in 1.55. Average roof height of structure with respect to base. Now, this really, it really doesn't matter too much because the tank is at ground level. But let's say the roof height, let's just say the roof height's at 10 feet. Just have an even number in here. You'll see it's not going to matter because the tank is at ground level, so the elevation of the roof is irrelevant. I'm going to hit print. I'm going to type in what it is I'm talking about here, and I'm talking about a horizontal air receiver tank. And as I mentioned earlier, the AP value is 1. WP, now that's the weight of the tank, and that was 1,671 pounds. I could enter this in kips, but for the system that I use, I enter it in pounds. And you'll see why later when I use my Excel spreadsheet. The Z value is 0 because this thing is sitting at ground level. The RP value, as I stated earlier, is 2.5. And the importance factor is 1.0, which you can read about that in chapter 13. But because it's just air that's inside this, that has an importance value of 1. Okay, so that's about it right there. You can see that it calculates a value of 777 for the component and 777 for the connection. So at this point we've finished up our work here in InterCalc. I'm going to hit print. I'm going to create a PDF. I'm going to save it to the location design information calculation report, temp calc for report. So it's just like a temporary calculation for my report. And I'm just going to call it S for seismic. Just a very temporary calculation. All I'm looking to do is get a screenshot on this and highlight that FP value. So I'm going to use my snipping tool again, come here, take a screenshot, and I'm going to highlight the FP value for the components as well as the connections, which they are the same value. I'm going to copy this and I'm going to paste it into my report. So I'm going to delete this table from a previous project, and then I'm going to paste in my new table. So there are the FP values for this project. So I'm going to change the name of this. I'm going to call it horizontal air receiver tank. And I'm going to put a screenshot in. I'm going to delete this old screenshot and put in my new screenshot for this current project. So I'm going to copy it out of PDF that was given to me on the project specs for this tank, and then I highlight the height and the width, because those will be important when it comes to the Anchorage design. So now I've got a picture of the tank in here, and you can see the next step here is this Excel file, which again, this is one of my templates, so I'm going to open up that template. So ABC Labs, design information, Excel calculation, seismic design equipment, Anchorage. So here is my Excel spreadsheet. So I'm going to start up here at the top, and I'm going to just start by putting the name of the unit in here. So it's a horizontal air receiver tank. And as I stated earlier, the weight of this thing is 1,671 pounds. So, and I need that in kips. So I'm going to say it's 1,671 pounds divided by 1,000. The SDS value for this site is 1.55. The FP value, which we got from InterCalc, is 777 pounds, which we want that in kips, so I'm going to divide that by 1,000. So the FP here is shown as 0.78. Okay, now the horizontal dimension between anchors. So that's why this screenshot here is important. So this picture is showing me that between the anchors we have 40 inches. So I'm going to put 40 inches in here. And then the vertical dimension to the center of gravity. Now, the picture doesn't necessarily tell me exactly where it's at, but obviously it's going to be somewhere about 25 inches. So I'm just going to put in 25. If I wanted to be safe, maybe I'd put in 26 or 27. But we'll see that there'll be a large factor of safety even with 25 in here. And the horizontal dimension to the center of gravity, we're going to say that's right there in the middle. It's at 0. It probably is. It might be off. It might be just 1 inch, maybe 2 inches. If you wanted to be safe, you could put an inch in here and say, well, the center of gravity is off by an inch. And so the white cells, those are inputs. The gray cells are calculations. So the vertical seismic force, that's going to be 0.2 SDS times WP, so 520 pounds. The rho value is 1. The overstrength, as I stated earlier, is 2. And the QE value that's calculated here is 0.78 kips. The EH value, 0.78 kips. EMH value, calculated 1.6 kips. So that's our horizontal seismic force that we have modeled acting on the tank, 1.6 kips, 1,600 pounds. And then what that results in is an overturning moment of 38.9 kip inches. And I'm going to put this to that center of gravity to 0. You know, to make things more accurate here. Alright, so we have an overturning moment of 38.9 kip inches, and we have a total of 4 anchors, 2 anchors per side. So here this Excel spreadsheet's calculating that the design tension in each bolt is 0.24 kips, and the design shear in each bolt is 0.39 kips. So essentially, what does that mean in real life? if we have a horizontal force acting through the center of gravity of this tank, it's going to want to cause anchors on the right side to go into tension, while all four of the anchors will also be put into shear as well. So there'll be a shear load on all four anchors, and then there'll be a tension load on the two anchors on the right hand side, and then vice versa. As the earthquake goes the other direction, these two go into tension. So that's essentially what's being calculated here. This is tension loads, shear loads, and then the slab, which we'll talk about later. For right now, we're just going to talk about the goal of this portion of the spreadsheet is to calculate the tension and shear that we're designing those bolts for. Now you can see that I did this very quickly. Previously, in years past, it took a long time to get here because I did not have a template generated. So we will go back to our report. We're going to take out this picture, and I'm going to paste in the new picture. I'm going to paste it in as a picture. That way it can't be modified. I don't want to put it in as text or a table. I want it as a picture. So here we go. This is what we're looking for. The tension and shear on the bolts that we're designing for. So at this point, we've got our table in here showing our tension and shear for each bolt. Now we are going to move on to designing the anchors. At this point, I'm going to do the structural calculations for the anchors. The software that I like to use is the Hilti Profis engineering software at this website here. I'm going to start by creating a new project. I'll just call it 2301 ABC. I'm now going to design the anchors, so I'm going to select anchoring to concrete because this tank is being anchored to concrete. This will be general construction. The base material, I'm going to start by assuming I have a 6-inch thick slab, which that's my standard slab for an application such as this. For the clearances, edge distances, I'm going to assume I have at least 10 inches, and I'll make sure I have 10 inches when I make my plans. But I always want to make sure I've got at least 10 inches on the corners to prevent the breakout. So we'll start by assuming we have at least 10 inches. Come down here to our anchor plate. We will not have an anchor plate. And we'll come down here and select a single anchor. So we're just going to analyze one single anchor. We're not going to analyze a group, we're just going to analyze the one anchor. As far as the load combination, as we discussed earlier, the load combination is this load combination here from ASC 716. I'm going to copy this out of the Excel spreadsheet. I'm going to paste it in here. This tells me, it tells the plan checker where these loads come from. And as we discussed earlier, the shear on each bolt is 390 pounds from the Excel spreadsheet. So I'm just going to put that in as 400 pounds, make it even. And then the tension on each bolt is 240 pounds. Now I'm also going to select the seismic design for the ACI 318 anchoring to concrete provisions for anchors installed in structures assigned to seismic design category C, D, E, or F. And this structure is in probably category E. So I've selected this. I'm going to come over here to load calculations, and I would like to, so as I had already selected here, seismic design, so I selected seismic design, and under this drop down I'm going to want to select item D. What does this say? If the anchor or group of anchors is being designed for the maximum tension load calculated with the earthquake load factor E increased by the overstrength factor omega naught. Yes. I do not want to re-input my load. So what does that mean? So when we made the Excel spreadsheet, we accounted for this omega naught, which is our overstrength factor of 2, which is basically saying that we're going to take all the loads that we calculated and increase them by a factor of 2. Likewise, for the seismic shear type, we're going to also select this item. Select this if the anchor or group of anchors is being designed for the maximum shear load calculated with the earthquake load factor E increased by the overstrength factor omega naught. Yes. Like I just said, we're using the omega naught factor, and these loads down here reflect that omega naught factor. I do not want to re-input my loads. Okay, so there we have it. We have our loads in here. We've specified it's a seismic load. We've increased them by omega naught in the Excel spreadsheet. Now let's specify the anchor that we want to use. So the anchor that I like to use is the Hilti QuickBolt TZ2. There it is right there. Okay, so I'm specifying the Hilti QuickBolt TZ2, and I know I need to use a 5/8 inch anchor because if I look at those drawings for the tank drawings tell me that there's a 3/4 inch slot. So for a 3/4 inch slot, I want a 5/8 inch bolt. So I'm a 5/8 inch bolt and an effective depth of 2.75 inches. So I could select this, and I could select some different. I could go 3 1/4. I could go 4 inches. But as you can see, I'm already passing at 2.75. I'm at 11%. If I go 3 1/4, I drop to 9%. So 2.75. That's plenty good enough. I'm only at 11% capacity. So there it is. We have a Hilti QuickBolt TZ2, 5/8 inch diameter, 2 3/4 inch effective embedment with these loads on it under seismic conditions. And so we're good with this anchor right here. So we're going to create our report. Actually, why is it showing 14 inches? Interesting. For the clearance around these bolts, I'm going to assume I have 10 inches. Maybe I forgot to update this. And this I'll verify once I do the drawing. So basically, once I draw this in AutoCAD, I'm going to want to verify that around each bolt there's at least 10 inches before you hit the edge of the concrete. And that's important for concrete breakout. Alright, so that looks good to me. We're going to create a report. I'm just going to call it AB for anchor bolts. Labs, design information, calculation report, temp calcs for report, and I'm just going to put it here. I'm now going to go to that PDF and I am going to turn this into a JPEG file. At this point, I'm going to export the anchor report as JPEG images. So I'm going to export to JPEG images. I'm just going to save it to my desktop under temp files. So I'm going to save those images there. I'm going to open up my report and I'm going to drag those images in. So that anchor report is 9 pages, and here's my report. And so, as we stated, 5/8 inch anchor bolts with 2 3/4 inch effective embedment, and a nominal embedment of 3 1/4 inch embedment, which we'll get to that more once we get to the CAD file. But here's our report showing our loads: 400 pounds in the lateral direction, 240 pounds pulling up. So now our Hilti report is in there. So the next thing that we will do is get into the AutoCAD file. So at this point I'm going to start by working on the plan sheet. So I'm going to jump into my AutoCAD files. Like I said, I have two template files. First one is a border file, and the second one is the main project file. So I'm always going to start with my border file. So I'm just going to name this 2301 BDR. So this here is the border file. I'm going to start by updating the project name, and I'm going to call it New Exterior Air Tank Installation for ABC Labs. And I will put the address, which I'm not going to put the address, I'll just put Pleasanton. And the zip code is 94588. Then as far as the building department, I will update the building department. And previously we had put it in as City of Pleasanton Building and Safety Division. Address. And the phone number. Okay, put who it. We'll then come over here and update who it's drawn by. Designed by and checked by. And this is project 2301. This is August 19th. And there we have it. Our border file is complete. As you'll see, anything here I have in purple is on a layer that I call no print, so I don't want it to print this. Same with I don't want it to print the sheet name. So my border file is good now. So hit Q save. I'm going to save my border file. And then go into my project folder, or project file. So I'm going to rename this one 2301, and I'll call it ABC Labs. So you can see here the first thing it prompts me for is to reload my XREF file, my border. So I'm going to say open XREF palette. So I'm going to come over here to that border file. I'm going to select new path. And I want it to come to 23, example projects, ABC Labs, plans CAD, original CAD files, 2301 border. There's the border file. So we have our border attached, we have the sheet name, equipment Anchorage, we have the sheet number S1, and one of the first things we can see is that the JPEG images that I have here are not loading. So I'm going to make sure everything's patched correctly. So I'm going to go XREF, and then adhesive. I'm going to select on this, select new path, and I'm going to path everything to the CAD file, Word Engineering CAD files, and then the references. So here are the references that I have active in the sheet. I want these to show up here. So I'm going to select adhesive. Now I found that here. I'll have to come here for the rest of these. So I'm going to reload all of these. Reload. Reload. Okay. Alright, so all of my images are referenced in. So you want to start with that. Alright, so starting up here in the top left corner, as I was talking about, my go-to anchor that I like to use is the Hilti QuickBolt TZ2. And as you saw earlier, we specified a 5/8 inch diameter Hilti QuickBolt TZ2 anchor. So I'm going to leave this table in here along with these notes that I had previously written here. Over here I've got other anchors if I'm using these, which I'm not for this project. So if I'm using screw anchors, I've got my screw anchor information here. If I'm using adhesive anchors, I have my adhesive information here. But for this project, these will not get used at all. So I could just kind of kick these off to the side. But if I were using a project that used either one of these, I would take these and throw them onto the sheet. Okay, so I'm going to leave this table here because I know I'm using a QuickBolt. These notes here, these notes won't change. These are current notes based on the 2022 code cycle. So we're going to leave these here. And then we're going to come down here to loading criteria, and we're just going to update this information right here. So I'm going to pull up my calculation report so I can get these values. Alright, so first of all, wind design data. So wind design data is irrelevant, right, because it's interior. So we say interior non-exposed risk category, and then risk category is 2. The seismic information is the information that really matters here. So based on that sheet that I printed out earlier, the SS value was 1.938. So we'll just go 1.94. The S1 value is 0.713. So we'll go 7.1. And SDS is 1.55. Site class is D. We use stiff soil. We do not have a report. The seismic design category for this project is D, and that information comes from ASCE 716, table 11.6-1. So anytime the SDS value is greater than 0.5, then you're in category D. The importance factor is 1.0. You can read about that in chapter 13 of the ASCE 716. Essentially the tank is holding air, which is not a hazardous material. And for our geotechnical data, we're going to say 1500 psf allowable soil bearing pressure because we do not have a report. Here are the standard codes that are applicable. Now we will move on up here to this table that I call the floor mount equipment anchorage schedule. So we're just going to give this tank a name here. And we are going to call it the horizontal air receiver tank. And the weight of it is 1,671 pounds. And as we discussed earlier, the anchor type that we're using a Hilti QuickBolt TZ2-CS wedge anchor. The diameter, we're going to be using a 5/8. We're going to change this to 5/8. And there will be 4 of them. And the nominal embedment depth, so that was stated in the report. So I'm going to go back and look at that report. So nominal embedment depth is 3¼ not to be confused with the effective embedment depth. So if we look at the report, the nominal 3.25, effective 2.75. So I like to state both just to help eliminate any confusion. And there's really no detail. So our floor mount equipment Anchorage schedule is complete here. So now I will move on over here, and what I like to do here is basically insert a picture of what the tank looks like and then point at the anchor locations and just make the statement Anchorage per floor mount equipment Anchorage schedule. Alright, so here's the path to the image here. So I'll select the image. And throw it in there like that. I'm going to take this and delete it. So this is just kind of a placeholder. So I'm going to take my image. I'm going to crop it and get rid of this isometric view. Crop that image a little bit here. Okay, I'm going to move it over. And then I'm going to scale it just a little bit, make it just a little bit bigger. Clean this up a little bit and put the text up here. I'm calling this a horizontal air receiver tank. Then I'm going to move this text over here, and I'm just going to point at the anchor locations. Generate all. Tools, draw, order, bring to front. Alright, so here we go. I'm pointing at the anchors. I'm saying anchor per floor mount equipment Anchorage schedule. Okay, so one of the things I like to use is I like to use tables. So that's why I put this information in a table. And I don't like to create unnecessary details. So I don't want to go like getting a block of that anchor and putting it in here and making unnecessary work for myself. I prefer to just take a screenshot from the plans, make a simple statement like this. It says, go look at the equipment schedule, and make it a lot easier that way. There's more than one way to do this, but this is the way I prefer to do it. Okay, so we've got this part done. We've got our anchors information over here for installation. We have our equipment Anchorage schedule here. At this point, I'm going to work on the foundation plan, which will be up here in the top right corner, which should really be the last item on this sheet that we need. So I'm going to come in here to the model space, and I'm going to do my work right in here. So the first thing I'll say about this is that I never really want to be the one driving the bus on where the tank is going or how big the pad is. So for instance, this is the drawing that was given to me by the architect, and so the architect has shown me that he wants the pad to be 6 feet wide by 13 feet 9 inches long. And then he's shown me 12 inches of clearance from the edge of the tank to the edge of the pad, which, thinking back to those bolts, how I assumed I had at least 10 inches of clearance, and here I have at least 12, so I'm happy with that. That's a side note. Okay, so essentially I want to take what the architect is showing me and I want to check this design. I don't want to be the one saying, oh, let's make the pad 8 feet long or 10 feet. Like, it's irrelevant to me. I don't really care. As long as it calcs out just fine, then I'm good. So we'll start with what the architect's showing me, and if I do my calculations and for some reason this isn't calcing out, then I'll let them know, hey, I need you to make this 7 feet instead of 6 feet. But I always want to start with what is it the architect wants. So this is what the architect wants, so this is what we're going to go with. So the first thing I'm going to do is I'm going to take a screenshot of this here, and I'm going to save this as a JPEG file that I can reference into the AutoCAD file. So I'm going to hit File, and I'm going to save it. I already saved it in here as floor previously. So I've already got it there as floor. So then I can come to my AutoCAD file, select image, and I'm going to detach it out, and I'm going to attach it in. So attach, and I'm going to come here to floor. So here's that screenshot I created earlier. And I'm going to put it in here, just like so. Alright, so I have the image in here. It's obviously not to scale. I want to get it to scale. So what I'm going to do is I'm going to draw a rectangle that's 6 feet by 13 feet 9 inches. So I'll type RECT, come on over here, type D for dimension, and then 6 feet, and then 13 feet 9. There we go. So if I check this, DI, 6 feet and 13 feet 9. So I'm going to take this, move it over to here, and I'm going to scale this image until that slab is the correct dimensions. So I'll type SC, select the image, select this point, type R for reference, select this point, come over here, select this point right here. I'm going to turn my O snaps off because I don't want it snapping to anything. Now I'm going to turn my O snaps on because I do want it to snap to right here. Okay, so that looks like it worked out very well. That's good. I'm going to move all this other garbage out of the way. Other things I've drawn, just standard stuff. Alright, click the properties on this. Right now I'm operating on the layer 02 paper space. I want my concrete to be on 20. Just my CAD standard that I like to use. Okay, so here is our slab. So 6 foot wide, 13 feet 9 inches long. Then I'm going to come over here and I want to, first of all, let's check this scale here. So it's standard scale, 1/2 inch equals a foot, which is what I previously had it set up as. I might have to expand this a little bit. Just messed it up there. Go back here, standard scale, 1/2 inch equals a foot. Okay, so here's our tank. I'm going to move this text out of the way. Going to lock the viewport so I can't mess up the scale on it. And what I'm going to do is I'm going to come to that image. Now there are other ways of doing this. If I had the AutoCAD file, I could paste in the AutoCAD file. Right now I'm putting in an image because that's just what I have. I prefer to put in the AutoCAD. If I have this that says AutoCAD, but I do not right now. I just have this image, so I'm going with this. I'm going to come to the image, fade this at about 50%, because I want the focus to be on the foundation information. And if I want to, I could extend this out. I'm really not concerned about cutting off this text, because that text is going to appear in the architectural sheets. So really the sheet only needs to pertain to just what information is needed for the contractor to build the foundation slab work. So we're going to start with this. We have our dimensions right here, 13 feet 9, 6 feet. So I don't need to duplicate those. I don't need to put any dimensions. If I didn't have those, I could throw some dimensions on there, but I'm not going to duplicate it. Alright, so first of all, I'm going to start with a few callouts here. So I'm just going to move these down here. So let's just start with that slab. So I'm just going to take this text here, concrete slab. I'm just going to point at that slab. Very simple. I could pull this a little closer. It's a little extreme. And then I want to point at that tank. I could probably just leave it right where it's at. So there's the tank. And then change, so this is just generic, so it's a horizontal, and then what is it? It's a air receiver tank. Now I need to provide the information on what is this slab, like how thick of it, what's the rock, etc., etc. So I'm going to move this text down, and I'm going to put this right over here. And I can move this whole thing over. So here, like I said earlier, my standard slab for a piece of equipment that's going on it, 6-inch concrete slab, number 5 rebar, 18 inches on center, 2 inches of sand, 4 inches of rock. The sand isn't necessary. The rock is, the visqueen is, because this is indoors. Alright, so that's looking pretty good. I might even bump up the weight of this concrete slab edge, so I might bump up that line weight. Instead of the 0.18 standard, I might go 0.4, just preference. Make it pop. And really, that's all that's needed here. I know this looks very, very simple, but in reality it is simple. It's just a concrete rectangular slab that's 6 feet by 13 feet 9 inches, and it has a tank sitting on it. And the tank location, exactly where it is on the slab, that's more on the architect. So you can see on the sheet, he tells you where it's going. So as far as the construction of it, the foundation plan, this is all the information that's really needed. Anything more than this would really just kind of be overkill, to be honest. So this is our sheet. Now, although I'm about, I'd say, 99% complete, I won't print the sheet until I've done the calculations that show everything's okay. So at this point, I'm assuming a 6-inch concrete slab is going to work. I haven't proven that it works yet, but I'm assuming that right now. Well, we'll get to the calculations. Once the calculations are final, then I final the sheet. That's the process that I go with. Alright, so we're going to step away from this and go back to our calculation report. So here we are back at our calculation report, and the next item here is the concrete slab. And so one of the things I said earlier is let the template be your guide. So the template walks you through the steps of the things you need to check. So now we're going to design the concrete slab. And as you can see here, I like to design my concrete slabs using InterCalc. But before we get to that, I'm going to input a few pieces of information here. So the dead load weight of the tank is, and that was 1,671 pounds. The tank is supported at 2 ends, therefore the dead load at each end is, and then so it'll be this divided by 2, which is 836 pounds. The support beam at each end is so many inches wide and so many inches long. Okay, so essentially what I'm trying to do here is I'm trying to come up with a linear load. So I need to get a load in pounds per foot or kips per foot that I can then put onto the slab and show that the slab is sufficient. So in order to do that, I first need to get these numbers. So this is the tank here, and the width of this little foot that it's sitting on is 2 inches, and the length is 42 inches. So I'm going to come back here. The support beam is 2 inches wide, and the length is 42 inches long. Okay, so with that information, we're going to hop back into InterCalc and do a calculation for the slab. So we come here to our project, ABC Labs. We're going to go to calculations, hit add. We're going to do under foundations, we're going to do point load on slab. Description, we'll call it slab for air tank. Now all of these can say the same except the compressive strength. We're going to say it's 2.5 KSI. That slab thickness, I said 6 inches. I'm going to use ASD. And I'm going to add a load here. So I'm going to just call this tank weight. Load support width. So we said earlier that was 42 inches. Or actually no, 2 inches. And then the length was 42. Okay, the dead load. So the dead load, that was the 836 pounds at each end. So that's 0.836 kips. We have no live load, no snow load, no wind load. Now we do have seismic load, but these are going in the vertical direction. So if I want to put a seismic load in here, what I would look to put in here would be this EV value. So this is the vertical seismic force, so 0.52 kips, and there are 2 ends to this tank. So if I want to take this and divide it by 2, and that's in kips, and so multiply this by 1,000, so 259 pounds. So I could put a seismic force of 259 pounds on this thing here. So I'll just say 0.26 kips. Okay, I'm going to hit save. Alright, so you can see here it does say pass. So here's the tank weight. The length is 42 inches, width 2 inches. Dead load was 0.84 kips. And we put a seismic load on there of 0.26 kips. So it's saying that the ultimate force is 1 kip and that it has a nominal capacity of 118 kips, so that more than passes. I am now going to print this slab calculation as a PDF. I'm going to save it to my temporary calculations reports, and I'll just call it slab. I will then go to the file, and I'm going to take a screenshot of this. I could export it as a JPEG, or I could just simply take a screenshot here. I like to just take a screenshot, a little bit simpler. And if I want to highlight something here, maybe I would highlight that the PU value is 1, the PN value, the nominal capacity, is 117 kips, and that the factor of safety is greater than 3, so it passes. So I'm going to hit Control C, open up my report here. Delete this section here and put in the calculation from InterCalc right here. And I previously already put this information in there, so I'm going to leave that alone. So here's my calculation for the slab. I am now going to move on and do the calculation for the overturning of the slab, which should be the last calculation in the report. So I'm going to set my report aside over here. I'm now going to turn back to the Excel spreadsheet that I was working in previously, and I'm going to work on this section down here at the bottom that pertains to the slab. So let's first start by realizing that the inputs are in white here and the calculations are in gray. So if everything works properly, then I really should only have to adjust these values right here and then look at the outputs and make sure everything's good. Alright, so let's start with the thickness of the slab. We said earlier that we're going to use a 6-inch thick slab. And then as far as the dimensions of the slab, the architect has directed me that he would like to use a 6-foot by 13-foot 9-inch slab. So we'll throw this off to the side. So we have slab width 6 feet and a slab length of 13 feet 9 inches. So we could say equals 13 plus 9 divided by 12. Alright, so we have our inputs here, and then let's just kind of take a look at what these outputs are. So this section here pertains to the overturning capacity. So you have an overturning moment, which is here, the 38.9 kips, which we previously calculated up here, 38.9 kip inches. That's trying to overturn the tank. Then you have the two items that help resist the overturning. Number one, you have the slab. So the slab has a weight to it, and that weight is wanting to prevent the system from overturning. As well, you have the equipment piece itself. And so that slab provides a resisting overturning of 200 kip inches, and then the equipment self-weight provides an overturning resistance of 54.1 kip inches. So if we add those two together, it comes out to 254.6 kip inches. That's our overturning capacity. And then you can see that, as I stated earlier, our overturning demand is 38.9 kip inches. And we divide those two, and it comes out with a factor of safety of 6.6. And since that's obviously greater than 1, then we say that that's an acceptable system for preventing the overturning. So we're happy with this. And here are just a few screenshots that provide some input on slab design. So from the California Building Code, 3.5 inches minimum, and then it gives some provisions regarding vapor retarders and then when they are not needed. And then as far as minimum reinforcement ratios, here's some information from ACI. So I like to put little screenshots of information, and it helps me understand where I got information from. So I'm going to copy this out of the Excel spreadsheet, and I'm going to put that into my report. So I'm going to delete this table out, hit paste, and there we have it. Here's our table. So it lets us know that the slab and the equipment together combine for create a system that prevents the overturning of the slab and the piece of equipment. So there is our report. Our report is complete. And we'll just, last thing I like to do is come back to the table of contents, update my table of contents. And then we can quickly just run back through this real quick. Project information. We do not have any geotechnical criteria to use. We're talking about one piece of equipment here that weighs 1,671 pounds. We're not considering wind because this thing is inside of a building. We're concerned about seismic, so we get our seismic information, namely our SDS value. Here are our parameters from ACI or ASCE 716. Here is the equation that we're using for calculating the horizontal seismic force on the tank. We use InnerCalc to calculate that FP value. You could create your own Excel spreadsheet. I like using InnerCalc. Here is the geometry of the tank that we're talking about. Most importantly, the height and the width between anchor bolts. Here is the Excel file table, which ultimately calculates the tension and shear in each of the 4 bolts. Here is our Hilti output, in which we imposed the tension and shear loads on the bolts and check to see that the bolts are adequate, which they are. You can see that the maximum ratio, I believe, was somewhere around 8% here, 12%. Then we moved on to designing the slab. So we have some information about the load from the tank onto the slab. We input those loads into InnerCalc, and everything checks out there with a factor of safety of about 117. Then we check the concrete slab for overturning, and considering the weight of the concrete slab and the equipment that's on it, it also has a factor of safety of 6.6, so this checks out just fine as well. So our report is complete. So I will save it. Save as Adobe PDF, and I will put it here in the calculations report. So now our report is complete. So I will go back to my AutoCAD file and ask myself, in the process of updating those calculations and completing the calculation report, did anything affect my sheet S1 here? And the answer is no. So we still have the same anchors. The last thing we were working on was our slab design. So we did our slab calculations and everything checked out. We had a 6-inch slab, and that worked out fine for the slab design as well as the overturning, so we're good with that. That would have been the main thing. If 6-inch slab didn't happen to work for some reason, then we would come here and we would update this number. But other than that, there was really nothing else that we were looking for that we were finishing. So we're good. We're using the Hilti Quick Bolt TZ2 anchors. Here's the Anchorage schedule, our standard notes, which are not changing for this project, our loading criteria, which this is project specific right here, which we updated this, our codes, we're using the 2022 California code cycle, and very simple foundation plan / slab design. And this is all that's really needed. Okay, so we're going to save this. We're going to make a PDF. Hit plot, preview, plot. Save this to the desktop. And there we have it. Our plan is complete. So here are our two deliverables. Number one, the structural calculations. It's PDF. That's 18 pages. And the plan sheet, which is a PDF and it is just one page. And that is all that will be needed to go to the building department and complete this project for the structural submittal. As I showed earlier, here is the Ward Engineering digital store where you can purchase the 4 template files that I used for this project. You saw in the video how they were used and how they can very efficiently help us get to the result that we're looking for without having to reinvent the wheel and create a lot of unnecessary work for ourselves. So again, we have the AutoCAD files. Number one, we have the border file, and then we have the working file. Then we have the Word document for the structural calculations report. And then we have the Microsoft Excel file, which calculates the tension and shear in the bolts, as well as checks the slab and equipment system for overturning. So that completes this video course. If you have any questions or comments or want to ask me any questions regarding these templates, I'll be more than happy to speak with you. With that being said, I hope you've learned something from this video, and I look forward to hearing your feedback. Thank you.